All right. Not very many announcements today. There is mastering due tonight. It covers the end of whatever chapter we're in, 18 and 18. Exam 3 is a week from today, unless you took it this morning, or you're taking it right after class. Your final, so you can put it on your calendar, May 5th, 10:30 a.m. in here, which is the Monday of finals. And if you're interested, there is an ACS study guide to help you prepare for the ACS final exam. It is for sale, the same place you get your goggles and lab notebooks and whatnot, in that room. It's not required. Maybe some people want to go in together and buy one. There's probably some floating around of the same study guides from last year, so you may know someone. They have them in the library on reserve.
So like hour, 2 hours?
Yeah, an hour or 2 hour checkout, so if you'd rather not buy one, totally fine. Just if you prefer to have it in your room.
No, I got the 108 one.
Yeah, it's the same book. It's the 108 one. Yeah, it's the same book as 108.
Oh, it is?
Yeah, it's just now the whole book is what you need to know for 109, where 108 was just selected chapters. So, all kinds of options for those study guides. And they're helpful in terms of like just reading practice problems. Yes, if you want to do that, you need to talk to me so we can get it sorted out. All right, so up until this point, we've been talking all about voltaic cells, which voltaic cells are the ones that are spontaneous and produce electricity. If it's a non-spontaneous cell, then it's an electrolytic cell. But we can use the non-spontaneous cell to still perform chemistry. It just means we have to add energy to the system to get it to work. I don't like that pen. Okay, this process so you use an electrolytic cell to perform electrolysis. So you've probably benefited from the use of electrolysis without even really knowing about it. For example, when you look to buy jewelry, right, it's either pure silver or it's silver plated. It's pure gold or it's gold plated. When it says plated, it means it's been plated using the process of electrolysis. It's a non-spontaneous reaction to put the gold on the piece of silverware you want to use or the piece of jewelry, but we can force gold to stick to it by pushing electricity through the solution. How else would you run into it? Right, if you have something that's chrome on your car, chrome plated, it's not chrome all the way through, it just means the outer layer is chrome. It's probably some sort of, most likely iron, that it's been plated to. I guess steel. Chrome-plated steel more likely than just plain iron, an alloy. When you think about tin cans, right, your regular tin cans, they're not actually tin. It's just they're tin plated. They probably at one point were tin cans, but now they're tin-plated steel cans because steel is cheaper. You plate them with the tin to prevent them from, like, the insides from eating away at the steel and rusting the can. So these are all times that you run into electrolysis. You just probably didn't think about it much. So if you wanted to plate an object, right, you wanted to put a coating on an object, we would want to know, amongst other things, we want to know how much silver or gold or whatever you're going to plate with. We want to know how much of that will be used. All right, because those are the expensive parts. The silver and the gold and the chrome, those are expensive. So you want to know how much you're going to use. So in order to do that, so I wrote really big on the other side. We need to have some new units to be able to determine how much material and how long to run the experiment. So first we're going to have a coulomb. So 1 coulomb, which is abbreviated C, is defined as a mole of electrons which a mole of electrons, using the long drawn-out explanation of how we get this, is 9.648 times 10 to the 4th coulombs. All right, and then we also need to talk about an amp, where 1 amp is a measure of current flow. And 1 amp equals 1 coulomb per 1 second. So it's a measure of how many moles of electrons are traveling. It's a rate, how fast they're traveling. And then when we talk about energy, what's the usual unit we use when we talk about energy? Joules. We can't use joules directly in these problems, right? Because we haven't had anything that refers to in joules. But it turns out 1 joule is 1 coulomb volt. So we have some new snazzy units that'll help us solve how much material to use and how long to run the experiments. So let's put it into use. So let's say I'm going to have a brand new chromium hubcap for my really boring car. Snazz it up so at least it has cool looking hubcaps. I could do this in the lab by doing some electroplating. Chromium can be electroplated onto surfaces through this equation. Chromium, is this taking place in acid or in base? Acid. And is this the whole reaction or is this the half reaction? It's only half. How do I know it's only half? I got electrons still in there. So this is the half reaction that refers to the chromium part of it. So when we do electroplating, we only need to know half the reaction, just the half we're interested in. So we solve these problems using unit conversions. So let's say I have a current of 8 amps and 3.5 volts. How many grams of chromium can be plated if I let the experiment run for an hour? So how do we solve these? Right, as we know, 1 amp equals 1 coulomb per second. So we're going to start with amps and get us into units that we can work with. All right, so starting with 8 amps. All right, just using my definition. So far, so good. What is something in the problem that tells me about seconds? So I can get rid of those seconds. It runs for an hour. Mm-hmm. 3,600 seconds. But yes, 60 seconds in a minute, 60 minutes in an hour, 60 times 63,600 seconds. Good. All right, so now I'm in the units of coulombs. And what was our definition of coulombs? Right, 1 mole of electrons is 9.648 coulombs. All right, now this is the reason we can only use half the reaction, because I need to move from moles of electrons to moles of chromium. So how many electrons are needed to do this half reaction? 12. How many chromium solids do I make? 2. So do I put the 12 electrons on the top or the bottom of this? Okay. So then how do I get from moles of chromium to grams of chromium? You need to know the molar mass, which happens to be 52.04 grams chromium for 1 mole chromium. Now you're ready, you can solve it. Let's see, 8 times 3 times 2 times 52. Okay, yeah, everybody gets something like that. Okay. All right, so these problems seem trickier than what they really are, but it's really just unit conversions. So everything we've done up to this point required a lot more work than this. So let me give you a little roadmap. So they're always going to be solved kind of in this order. You're going to have your amps. Amps go to coulombs. Coulombs go to moles of electrons. Moles of electrons will tell you about grams of, in this case we're plating chromium, it could be silver, or gold, or whatnot. And then from grams, you go to, or from moles, then you go to grams. So the problems are going to try and trick you. They're going to give you a lot more information than what you really need. Right? Did we use the volts on the other side? No, we didn't need them. Useful. Useful if I was going to do it experimentally, but it doesn't tell me anything about the grams needed. So let's try my other problem. Let's say you want to give the brand new baby in your life, cousin, niece, nephew, whatnot, a silver baby spoon, right? A traditional baby gift, right? Because the baby's born with a silver spoon in his mouth, right? That's a silver spoon. Anyway, you got to plate it because all you have is a boring steel spoon. So you've decided you're going to electroplate it with some silver. Why not? It'd be a very personalized gift if you silver plated it yourself. So let's say I have a baby silver spoon and I know its area, and I'm going to plate it with silver chloride using 2 amps for 2 1/4 hours. Why not? If the current efficiency is 82%, how many grams of silver got plated onto my spoon? This is as tricky as I can make them. It seems like a lot of information. All right, here I have silver chloride. Oh, I forgot my charges. Nope, no, that's right. Okay, silver chloride, silver solid, Cl minus, good. So, first thing we need to do is start off with our amps. Right, and it's 1 coulomb. I guess I want to do it this way. Coulomb second per 1 amp. All right, what do I need to do now to that 2 1/4 hours? I need to change it to seconds. So we're going to do it as a side note up here. Anybody double check that? Is that right? I think that's right. Okay. All right, so now I have my seconds. All right, so now I'm in coulombs. I need to go to the moles of electrons.
Is that a conversion factor same as Faraday's constant?
Yes, very similar. All right, now I'm in moles of electrons. What does my half reaction tell me about the electrons to silver ratio? It is 1 to 1. Let's see, silver has a molar mass of 107.9 grams per 1 mole. So let's solve that first, and then we'll worry about this. So let's figure out how many grams that is. Something similar to that? Everybody get something in the 18 range? All right. What am I saying if I made 18.1 grams. What efficiency is that? 100%. But I'm saying I only made 82%. So how do I figure out what 82% of this is? That is as tricky as I can make an electroplating question.
So that's 6.25 centimeters squared, and you don't need that.
No, not useful. But I throw lots of other things in there just, I mean, right, because it's going to be the same way every time. I thought maybe I'll make it tricky. That's it. That's it for levels of trickiness. So I would need 14.8 grams of silver to make that reaction go, which is a lot. So I probably won't do this. I'll probably just buy a silver baby spoon. Questions about electroplating? No. All right, that ends chapter 18, which we've been in for about 3 weeks now. It's been a long, long chapter.
Now our labs, we should actually silver plate things.
I'll see what I can do about that. It would be fun. It would be fun. Probably expensive. Very, very expensive. I may have to start charging per lab if that's what we start doing.
Well, there's an extra $1,000 in tuition exchange. Towards that.
Probably not, because that goes towards increased power bills.
And the fact that our wages are.
And, well, yeah, if our wages increase up to anything more, then the college is in trouble. Especially if it goes to $10 an hour, which they're talking about.
It's minimum wage, they raise minimum wage.
Yeah, if they raise minimum,
Wages have to go up.
yeah,
From like,
Well, they raised tuition $1,600 again.
which makes up for the fact that minimum wage went up, because everybody who has a student job, now we have to pay you more, which means you have to pay in more so we can pay you more.
So we're basically paying ourselves.
Yeah, have you never thought about that? You definitely pay yourselves.
So what's the point of like?
well,
The experience.
That's why you should work, because then you get that money back.
You get that money back.
Is it
Yeah.
true that they're getting drones to monitor the deer here?
Yes. Yep.
What are drones? Oh wait, I know what those are.
Yeah, so the little tiny helicopters, what they're going to do, well, they tried like actually implanting them and figuring out where all the deer migrate to. But partly, like well, they kind of know, right? But there's how many thousands of deer on campus?
Why do they need to know where they migrate to?
Well, because our deer never get hit by cars. So where are they going? Yeah, well, okay. In general, they rarely get hit by cars considering how many thousands of deer are on campus. So that's one of the things Dr. Gallagher's working on. The other thing he's looking at is if we start moving to all drone technology, like your Amazon package actually gets dropped off at your dorm room using a drone, which Amazon's planning on doing.
That's terrifying.
How are those drones going to affect the wildlife on campus? Are they going to freak out? Are they not? So he's just trying to figure out, trying to preemptively figure out. It's like those little tiny helicopters. I don't think they have cameras, but I could be wrong.
Stop, don't even go there.
But yeah, they could. Amazon is planning on no longer using the mail service. It's going to,
Well, Amazon's freaking crazy.
yeah, well, I mean, yeah, so I mean, Google just patented contact lenses that have computers in them. So like Google Glass is now old news. It's now in your contact. So whatever you're looking at, you are filming. Whatever you're looking at, you are face recognition. Whatever you're looking at, it is downloading information about. So that is the next step of Google technology. You need to start reading the news. Yeah, it's kind of frightening. Yeah. We are becoming a sci-fi movie. I mean, if you've ever been on Facebook, right, and you upload a photo, it knows exactly where the face is, and then it offers some suggestions. Yeah, so we're one step away from that with the contact lens that you can walk up to someone, Google will search its images and be like, oh, this person's name is Susie. Well, you can't remember. Yeah, when I meet all my students, I'm like, your name is, hold on. Okay.
Or when you're on a test, you're like, man, I can't remember. Oh yeah, just.
That is going to be an issue that we'll have to figure out because because you can, in theory, like if you wore Google Glass, you could ask it to search the right equations for you.
Why is that a bad thing? I mean, if you can use it in here, then you can use it out.
That's going to be
Just with your brain, like you say.
right now. You have to speak to it. Yeah, right now, like if you have Google Glass, you have to say something to
You
it.
can't talk out loud unless I have like a little telephone thing.
Yeah. So I mean, it's coming. It's coming. We have to figure out how to preemptively. It's so stressful. I know. I'll have to I'll have to pat everybody down. Be like, I'm sorry. Can everybody take out their contacts? Cody. Well, Google Glass right now, they're on sale if you want Google Glasses. They are on
You
sale.
actually have Google glasses.
I don't. But you can buy them right now. They're for sale for $1,500.
And what does it do?
It's like having your cell phone. You speak to it. Yeah, it's having Siri on your face. That's exactly what it is. You can talk to it. You can take pictures.
Although you can't go into a movie theater with Google glasses on.
Right.
Because then the authority has
Yes.
copyright infringement issues.
It is. There's a big debate whether or not you should be able to drive with it, because it's like having your cell phone in front of your face the whole time, where you can be talking and texting with your glasses on while driving. It could be a distraction. So, questions, all kinds of good ethical questions you guys should be deciding where you stand on. It is. And so it's probably going to come up for a bunch of votes. Now you guys are eligible to vote. There's going to be some big questions about, should you be allowed to drive with Google Glass? Should you be allowed to go into the voting booth with your Google Glasses on? A voting booth, right? Because that's considered private, who you vote for. But if you walk in with your Google Glasses and you can monitor everyone who's in there and kind of figure out what you're voting for, who they're voting for.
How do you do that?
It's just a video camera. It's a video camera on your face. Everywhere you're looking is recording. And it can send it back to Google. It can send it back to Google because you saw it, like when you click those accept things, you're really accepting a lot that you probably, right, because the scroll through the accept thing, most people just say whatever. It is. So there are some good things. It is. Yeah, there's a few people on campus who have them. You just buy them. $1,500.
Well, and on the computer, they now
Yeah, funny enough, when I upload this onto YouTube, it does ask me, like, where was this recorded? Would you like to tag anyone in it? Yeah. Cody. I think it's connected to your wristwatch. I think because it has just the circuitry in it to record, but I think it's controlled by, like, you know those new cell phone watches? Something like that. Send it to your watch, and then it wirelessly uploads it to wherever you want to go, the cloud.
She's lying. I'm not, she's lying.
I know. They are. I mean, they already have wristwatch phones, right? I mean, they have those. So they have wristwatch phones.
like to be on with this.
It's a phone that's on your wristwatch, so you can just talk to people. It's a little weird. It's supposed to connect to a Bluetooth so that you wouldn't talk like this. You would have your Bluetooth in, and they would hear you through that. But yeah, you guys need to read up on your news. Craziness. Privacy laws. I think they're probably trying to preempt it.
One of the guys said,
Right. The other issue is battery life. That, right, your cell phone's huge because it's a battery. If we can miniaturize the battery, then it could just be all in your contact lens. Just walking around with it.
how cool would that be?
You'd have weird glasses on your face.
So?
No, I have glasses too.
With the Google Glass,
When they
yeah.
can make Google Glass.
Google Glass.
Who has these on campus already? Because I haven't seen these things.
I know for sure Zane has the computer creative technology guy.
I'd be okay with
And maybe Dean Grout. I'll pass. They're around. It's the same kind that it's like the droid, same technology the droid runs off of. Because all it is you have them on and you say Google search, and it goes boop, 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 and then you tell it what you want to search, and then it scrolls the information in front of your face. No, it recognizes the words Google search.
Oh my God.
In theory, yeah.
Clear my chat.
That's a big question.
Because then you can just Google everything. I was looking at that. Yeah, you can get a prescription.
You can now. Yeah.
I just read. I'm
So weird. I want to go back to older days. And like, yeah.
Olden days before technology. Back when I was a student. Yeah, back when I was a student, when I got my first email address, it's pretty exciting. All right. How about like for the next 10 minutes, we'll talk about some nuclear chemistry, and
Kaboom. That's what's
yeah. All right. So, how many people heard about the Fukushima disaster that was, I guess, at this point, 24 months ago? Oh my gosh, Fukushima, the nuclear plant in Japan. Okay. We're going to talk about the technology that led to some of their issues. Obviously, you can't really prevent a tsunami. So they had things going against them, but there were some steps they could have taken to prevent the nuclear waste and radioactiveness from spreading everywhere. So we're going to talk about what exactly is going on in a nuclear plant and the atomic level, then we'll move up to the actual plant, and then we'll talk about some of the different nuclear plants, because, right, there's a nuclear plant being built in South Georgia. So we're going to talk a little bit about what are the implications of that. And there should be one in Alabama, which are the two nuclear plants that have been built in the past 20 years or so. Yeah.
So is this on our test?
Just the very beginning of this. I'll tell you where it cuts off. So, and once you see what we're doing, you'll be like, super easy. It's mostly identifying isotopes. So, which is a good review, because that was in 108, right? Isotopes. All right, so radioactivity was discovered in 1896 by Becquerel. And then further work was done by Marie Curie and Ernest Rutherford on what exactly is going on when we talk about it being radioactive. So these scientists, and there was a bunch of others obviously working in the same area at the same time, but found that certain nuclei are unstable and will spontaneously decompose. So the process of decomposition and then the emission of energy that goes along with that, that all falls under the category of radioactivity. I wrote really big, so I'm going to flip this over real quick. I'll wait for everybody to catch up. If it spontaneously decomposes, what's its delta G, positive or negative? Negative. Good review. Just checking. Good. All right, so radioactivity. There are 4 types of radiation that we're going to talk about. First one's going to be alpha decay, which that's the letter alpha. Beta decay. Gamma decay, which in the Greek alphabet that is the next letter, alpha, beta, gamma. Fun fact. I know you don't. At the school I went to had lots of fraternities and sororities, and so every year at the fraternity sorority talent show, they'd always sing the Greek alphabet as like the opening act with dancing. So it stuck in my head. I wasn't in the sorority. They're too expensive. At least they were at the school I was at. Ridiculously expensive. All right, and then positron emission will be the last one. All right, so let's at least do isotope review for a few seconds. All right, this should seem familiar, right? That you have the symbol X, which is the element symbol. And there's a mass number and the atomic number. Actually, let me back up. What are the three types of particles within an atom? Electrons, protons, neutrons. Okay, what's the charge of the electron? How about the proton? Okay, what about the neutron? Okay. Which two of those have significant mass? Protons and neutrons have significant mass compared to the electron, right? The electron weighs practically nothing. So when I talk about the atomic number, what type of particle is that telling me about? All right, the atomic number tells me numbers of protons. What two components are in the mass number? Protons and neutrons, okay? If I change the number of protons, what have I done to my element? I've changed the element, right? Number of protons is the thing that tells you which element it is. What if I change the number of neutrons? I'm now an isotope, okay? So let's say, for example, I have that guy. How many protons are in neon? How many neutrons are in neon? How many electrons? 10. Good review. Yeah, feeling confident? Let's do one more. Let's do one of these elements we're going to talk about later. Does anyone know which element PO is? Polonium. Polonium. It's one of our radioactive elements we're going to talk about. So how many protons are in polonium? 84, so a lot, right? How many neutrons? Yeah, whatever's left, a ridiculous amount, 128. Yeah, on the math skills, good. So a lot of neutrons. There's a lot of options of how many neutrons I could take away or give to it, right? Because there's way more neutrons than protons. And we have 84 electrons. Good warm up. Okay, let me give you some shorthand, I guess, up here in this corner. if I have this, what does my little p stand for down here? So it's still protons. What is this? If I say its atomic number is 1, how many protons does it have? What's its total mass then? 1 also. So I'm saying a proton has 1 proton, and its total mass is 1. So this is another way of writing out more officially what the proton is, right? I'm saying 1 proton's in a proton, and its total mass is 1. If I wanted to do that for a neutron, what would a neutron's atomic number be? 0. What would the total mass be? We're going to use these, as you can guess, in some balanced chemical equations, right? Because I'm either going to take away neutrons or give them protons, some kind of combination, so we have shorthand for it. What about my electron? What would its atomic number be? -1. Yeah, you can think about it in terms of charges. Right, because the proton has a +1, neutron's 0, electron's -1. You can think about it in terms of charge. But it has no mass compared to everybody else. All right, we will stop there. A little bit of stuff on Monday will be on the test. Very little. We'll do just one topic. That'll be on the test. Just alpha decay. Just that guy. And for your homework,